From protostar to true star occurs when the central temperature becomes high enough to initiate hydrogen fusion. This temperature threshold is approximately 10 million Kelvin. Reaching this critical temperature is entirely dependent on gravity's continued compression of the protostellar core. As the protostar contracts under its own weight, the central density and temperature steadily increase until nuclear fusion becomes possible. The time required to reach this stage depends primarily on the mass of the protostar. More massive protostars evolve more quickly because their stronger gravity leads to faster compression and heating. For a star similar in mass to our Sun, the journey from initial collapse to the onset of fusion takes approximately 50 million years. More massive stars can reach fusion temperatures in as little as 1 million years, while smaller stars may take over 100 million years. This difference in timescales has important implications for stellar evolution and the observed properties of star-forming regions. In clusters, we often see massive stars already on the main sequence, while lower mass stars are still in their protostellar phase, a direct consequence of gravity's stronger effect on more massive objects. The ignition of nuclear fusion marks a pivotal moment in a star's life. It finally achieves a stable balance between the inward pull of gravity and the outward push of pressure generated by fusion reactions. This balance, known as hydrostatic equilibrium, allows the star to maintain a relatively stable size and temperature for millions or billions of years. The pressure generated by fusion counteracts gravity's pull, preventing further collapse. This equilibrium represents a delicate balance. If the fusion rate increases, the star expands slightly, which reduces the central temperature and pressure, causing the fusion rate to decrease again. Conversely, if fusion slows, the star contracts slightly, increasing temperature and pressure until fusion increases. The achievement of hydrostatic equilibrium signifies the star's entrance into the main sequence phase, the longest and most stable period in a star's life. During this phase, gravity continues to play its essential role, providing the pressure necessary to maintain fusion at the star's core. Without gravity's constant inward force, the outward pressure from fusion would cause the star to expand and cool, shutting down the fusion process. The stable main sequence phase of stars like our Sun lasts for approximately 10 billion years, a period of relative constancy made possible by the perfect balance between gravity and fusion pressure. One of the most fundamental aspects of stellar astrophysics is that a star's mass, determined by the amount of material gravity has pulled together, largely dictates its entire life cycle and properties. More massive stars have stronger gravity at their cores, leading to higher central temperatures and pressures. This results in more rapid and energetic fusion processes. A star 10 times more massive than our Sun might burn through its hydrogen fuel in just 20 million years, compared to the Sun's 10 billion year lifespan. The intense fusion in massive stars also allows them to fuse heavier elements than lower mass stars can achieve. The mass of a star determines not just its lifespan, but also its luminosity, temperature, color, and ultimate fate. Very low mass stars, less than about 0.5 solar masses, burn their fuel so slowly and efficiently that they can shine for trillions of years, albeit dimly. Stars between about 0.5 and 8 solar masses will eventually become red giants and end their lives as white dwarfs. Stars between 8 and 20 solar masses will explode as supernovae and leave behind neutron stars. The most massive stars, those above about 20 solar masses, will also explode as supernovae but may collapse completely to form black holes. These diverse outcomes are all determined primarily by the initial mass of gas that gravity gathered together. Gravity also sets both the upper and lower limits for what we recognize as stars. On the lower end, objects with less than about 0.08 solar masses, or 80 Jupiter masses, cannot generate sufficient gravity-induced pressure and temperature in their cores to sustain hydrogen fusion. These failed stars, known as brown dwarfs, represent objects where gravity was strong enough to cause collapse, but insufficient to create a true star. Brown dwarfs occupy the mass range between the largest planets and the smallest stars, highlighting how gravity creates a spectrum of astrophysical objects. At the upper end of the scale, stars above about 150 solar masses are extremely rare and may be unstable. The immense radiation pressure generated by such massive stars pushes outward so strongly that it nearly balances gravity, causing the star to lose mass through powerful stellar winds. This suggests a practical upper limit to stellar masses, beyond which additional material cannot be held together by gravity against the star's own radiation pressure. The observation that stars exist within this mass range, neither too small nor too large, underscores gravity's role in defining what a star can be. Throughout a star's life, there exists a continuous battle between gravity pulling inward and various forms of pressure pushing outward. Initially, thermal pressure from the gas particles opposes gravity. Once fusion begins, the energy released creates a much stronger outward pressure that balances gravity's pull. This balance isn't static, but dynamic. Slight variations in fusion rates or gravitational compression are constantly occurring, with the star making minor adjustments to maintain equilibrium. For main-sequence stars, this balancing act creates remarkable stability over billions of years. The balance between gravity and pressure also explains many observable features of stars. The size of a star represents the exact point where these forces balance. Stars with stronger gravity, more massive stars, must generate more internal pressure to achieve equilibrium, which requires higher core temperatures and more rapid fusion. This explains why more massive stars are generally hotter and more luminous. The surface temperature of a star, which determines its color, is also indirectly determined by this balance. More massive stars with stronger gravity require hotter cores, which leads to hotter surfaces. When balance shifts, stellar evolution. As a star ages and exhausts the hydrogen fuel in its core, the balance between gravity and pressure begins to shift. With less fusion occurring in the core, gravity temporarily gains the upper hand, causing the core to contract. This contraction generates heat, raising the temperature in a shell around the core high enough to ignite hydrogen fusion there. The energy from this shell fusion causes the star's outer layers to expand dramatically, turning the star into a red giant. This expansion represents a new equilibrium state where shell fusion generates enough pressure to balance gravity across the star's greatly increased volume. For stars like our Sun, the core eventually becomes hot enough to fuse helium into carbon and oxygen. More massive stars can continue this process, fusing increasingly heavier elements in their cores as they evolve. Each transition to a new fusion stage represents a readjustment of the balance between gravity and pressure. Eventually, all stars reach a point where nuclear fusion can no longer generate sufficient pressure to counteract gravity. At this point, the final collapse begins, with the outcome depending on the star's mass. This final gravitational victory over pressure determines whether the star becomes a white dwarf, neutron star, or black hole. End-stage stars, gravity's final victory. White dwarfs and electron degeneracy. For stars with masses similar to our Sun, up to about 8 solar masses, the end of fusion doesn't mean immediate collapse to a point. Instead, these stars shed their outer layers as planetary nebulae and leave behind dense cores known as white dwarfs. In white dwarfs, a new form of pressure called electron degeneracy pressure prevents further gravitational collapse. This quantum mechanical pressure arises from the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. As gravity compresses the star, electrons are forced into higher energy states, creating an outward pressure that balances gravity. White dwarfs represent a new equilibrium where gravity is balanced not by fusion, but by quantum mechanical effects. Typically about the size of Earth, but with a mass comparable to the Sun, white dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons. There is a limit, however, to how much mass electron degeneracy pressure can support, approximately 1.4 solar masses, known as the Chandrasekhar limit. Beyond this mass, gravity would overcome even electron degeneracy pressure, leading to further collapse. White dwarfs slowly cool over billions of years, gradually radiating away their thermal energy while maintaining their size due to degeneracy pressure. Neutron stars and black holes. Extreme gravity. For stars between about 8 and 20 solar masses, the end comes more dramatically. After a supernova explosion, the remaining core collapses until even atoms are crushed. Electrons combine with protons to form neutrons, and the resulting neutron star is supported against further gravitational collapse by neutron degeneracy pressure. Neutron stars represent one of the most extreme objects in the universe, typically only about 20 kilometers in diameter, but containing 1.4 to 3 solar masses. The gravity at their surface is so intense that it curves space-time significantly, and their density is comparable to that of an atomic nucleus. For the most massive stars, above about 20 solar masses, even neutron degeneracy pressure is insufficient to halt gravitational collapse. In these cases, gravity achieves its ultimate victory, crushing all matter to a singularity and forming a black hole. Black holes represent regions where gravity is so extreme that nothing, not even light, can escape from within the event horizon. They are the ultimate expression of gravity's power in the universe. Objects where our current understanding of physics breaks down in the face of gravitational forces. The formation of these different stellar remnants illustrates how gravity, depending on the initial mass of the star, leads to dramatically different endpoints in stellar evolution. Modern observations and studies of gravitational collapse. Technological advances in observing star formation. Our understanding of gravity's role in star formation has been dramatically enhanced by modern observational techniques. Infrared and radio telescopes can peer through the dust clouds that obscure optical light, allowing astronomers to observe protostars in their earliest stages of formation. Space-based observatories like the James Webb Space Telescope provide unprecedented views of star-forming regions throughout our galaxy and beyond. These observations have confirmed many theoretical predictions about gravitational collapse and revealed new complexities in the star formation process. Interferometric techniques, which combine signals from multiple telescopes to achieve extremely high resolution, have allowed astronomers to observe the rotating disks around forming stars and even detect gaps in these disks where planets may be forming. Polarimetry observations reveal the orientation of magnetic fields in star-forming regions, helping us understand how these fields interact with gravity to influence collapse. The increasing sensitivity and resolution of these instruments continue to provide new insights into the details of gravitational collapse and star formation. Computational models and simulations. Alongside observational advances, computational models have revolutionized our understanding of gravitational collapse. Modern supercomputers can simulate the collapse of gas clouds in 3 dimensions, including the effects of turbulence, rotation, magnetic fields, and radiation. These simulations allow astrophysicists to model processes that occur over millions of years and observe how changing initial conditions affect the outcome of star formation. They have revealed the importance of feedback processes, where energy and momentum from forming stars affect the surrounding gas, potentially triggering or suppressing further star formation. Computational models have been particularly valuable in understanding how fragmentation occurs during collapse, and how this leads to the observed distribution of stellar masses. They've also helped clarify the roles of various physical processes in star formation, from large-scale gravitational instabilities to small-scale turbulent fragmentation. As computing power increases, these models become increasingly sophisticated, incorporating more physics and higher resolution to provide an ever more detailed picture of how gravity transforms interstellar clouds into stars. Conclusion: gravity as the cosmic architect. The formation of stars represents one of the most fundamental processes in the universe, the transformation of diffuse gas into compact, fusion-powered objects that produce the elements necessary for planets and life. Throughout this entire process, gravity serves as the primary driving force, the cosmic architect that shapes the evolution of matter in the universe. From the initial instabilities in interstellar clouds to the final collapse into stellar remnants, gravity's influence is constant and decisive. The process begins with Jean's instability in cold molecular clouds, where gravity overcomes pressure forces to initiate collapse. As collapse proceeds, conservation of angular momentum leads to the formation of rotating disks around protostars, setting the stage for planetary system formation. The continued compression by gravity eventually raises central temperatures to the point where nuclear fusion can begin, creating true stars that achieve a balance between gravitational compression and fusion-generated pressure. This balance defines stars' properties and evolution until eventually, fusion can no longer counteract gravity, leading to the formation of white dwarfs, neutron stars, or black holes. Our understanding of gravity's role in star formation continues to evolve as new observations and computational models provide increasingly detailed views of these processes. Yet the fundamental importance of gravity remains constant. It is the force that, over cosmic time, has transformed the universe from a nearly uniform distribution of gas, following the Big Bang, into the rich tapestry of galaxies, stars, and planets we observe today. In studying how gravity forms stars, we gain insight not just into astrophysical processes, but into our own cosmic origins. The stars that gravity built provided the elements that eventually formed our planet and ourselves, making gravity truly the force that connects us to the cosmos.